Hello, my name is Juan Cosme. I'm going to be talking about nanoimprint lithography. Some of the content that we'll be presenting on this video, uh, it will be including a brief introduction. We'll have a background information. We'll have types of nanoimprint lithography. We'll have some research examples. We'll have challenges of those research examples, and as well we'll have some challenges in nanoimprint lithography. We'll have a brief summary and conclusions, and then we will show the references used on this presentation. So, as an introduction, lithography. What is lithography in general terms? So, lithography is the process of imprinting an image directly from a plate, or it can be transferred to a flexible substrate like rubber for printing and publication. So, some examples of this, it will be this here on the left. So this is a lithography stone and its mirror image um, of a map of Munich. Okay, and here we have a 1902 lithograph map. So both of these maps were created using the lithography process. Okay, so nanoimprint lithography, it was introduced by the Professor Chu and his team in 1995. So NIL, as a short term for nanoimprint lithography, it has been demonstrated in as a really simple, low cost and high throughput process to replicate nanoscale patterns. The key here is simple, low cost, and high throughput. This is a process that you might have other processes that can produce similar uh, products, but they will not have that high throughput, that simplicity, and that low cost that the nanoimprint lithography process has. So some background information. So the question that I have to be popping into your minds right now is, what is nanoimprint lithography? What is NIL? So it is a lithographic technique that is capable of create patterns in the nanometer scale. It imprints a pattern on an imprint resist that is typically a polymer. So pretty much in the NIL process, a prefabricated mold containing an inverse of the desired patterns is pressed into a resist-coated substrate to replicate the patterns via mechanical deformation. So that mechanical deformation, it will be right here, as you can see. So this nano imprint lithography process is pretty much like a stamp process, so you can replicate it as you may want or as the process will need. So many replications may be produced from this, as you can see here on this image, or as the process will need it. So here this picture is showing two of the uh, fundamental types of nanoimprint lithography. So this first one is showing the thermal nanoimprint lithography process. So it works with thermal conditions, and here we have the ultraviolet nanoimprint lithography, that is also known as UV nil. So we will be expanding a little bit more on the next slide. So as I just mentioned, so we have two types of nanoimprint lithography. So when we are talking about resist curing, okay, so these two variants of the fundamental types of this process are thermal nil and ultraviolet nil, that is UV nil. So the thermal nil pretty much what it does is that so you have an imprint mold that it's typically is a mirror image of what you will want, right? And you will just print that, like pushing it into a thermoplastic polymer resist. So, but while you are pressing into it, you will be applying some heat as well. So the temperature is going to be about above that of transition temp. So after that, you let it cool and then you let it separate, and then you will have your imprinted image, right? So on ultraviolet nail, UV nail, so you will have that same imprint mold, but now instead of being using a thermoplastic polymer resist, you will be using a photopolymer resist. So you will press it, and instead of press it and putting some heat into it, you will press it and you will expose it to ultraviolet light. And that's all done on room temperature, okay? So after that, you don't need to let it cool or anything. You just separate it, and that's it. So now talking about some types of nano imprint lithography. Um, but now talking a little bit more of the imprint contract environment. So this is a different environment as the first one we discussed. Um, here we have three types of those of that process. So it's plate to plate, that is P2P, nil. We have roll to plate, R2P, nil, and roll to roll, nil. So the plate to plate, it's pretty straightforward. So a rigid flat stamp or mold, that is pretty much typically it's a pattern wafer, is used to imprint into a resist layer on a flat rigid substrate, resulting on an area of contact. So here you can see that that area of contact is huge. That means that you'll need a lot of force coming from here to create that imprint, to compensate for that huge area of contact. So in general, P2P nil may be conducted in two different manners: single step imprinting and multiple step imprinting. Now, talking about roll to plate nil, R2P nil. Um, so contrary to the plate to plate, now you have a roller press mechanism that is used to provide the imprinting force onto a rigid surface as shown previously on this image here. So on this image here, you will see all of that area of contact, right? So here now on the roll to plate one, you just have a roll and you only have a line contact right here. So what this do, or how this help? So since the roller press mechanism is utilized in a roll-based nail, the actual contact area during imprinting is only a line along the roller contact with the substrate rather than the entire stamp area as shown on the plate to plate. This reduces the entire imprinting force required in the process. Now the third and last type that we will be discussing here is a roll to roll. So the roll to roll nil process. So instead of having one plate, so we'll be using two rolls. Okay. So an imprint roller with pattern surface or wrap with a flexible mold is used to imprint onto a flexible substrate on a supporting roller instead of a flat plate in uh, roll to plate nil process. So you can see, so here we have, this is where we're imprinting on the roll to roll. Here is where we're imprinting on the roll to plate, and on this left one we have what we are doing on the plate to plate. Okay. So some research examples, This first one, I'm really passionate about photonics and optics. So I kind of focus my project or focus this presentation on those topics. Okay, so this first one, it's talking about just how some tiny three-dimensional structures are nano-imprinted at the end of an optical fiber. So some researchers um, demonstrated that the highest lithographic accuracy achieved in the latest years of an imprinted three-dimensional um, image at the end of an optical fiber. What is the most interesting thing here is that the end of that optical fiber, it was of the size of a human hair. So it had the thickness of a human hair. Okay, so those structures that they got to imprint on the optic uh, are able to manipulate the light properties, and these are the phase and the waveform, which are essential for integrated optic applications like laser matching, laminate fiber, some biomedical sensors. This allows for less expensive production compared to previous fabrication methods. Okay, so some techniques like electron beam lithography or focused ion beam milling, those are so expensive and time consuming. So, and they have a lot of limited development and limited use of optical devices integrated in a fiber. Another research example, it's more on photonics. So, photonics, it does have a whole gamut of applications that share common manufacturing needs. So, direct writing methods have been the preferred for research and development of optical structures, but these techniques are not the preferred ones for cost-efficient production applications. So, there exists a step and repeat optical lithography systems that are also called steppers, which are cost effective for high volume production, but they're not designed for photonics industry, but they're for electronics industry. So nanoimprint lithography, what it does is that it bridges the gap between research and development departments and high volume manufacturing. So Neil is the best suited lithography technique that can adapt to the needs of the photonics industry. The full-field ultraviolet version of the nanoimprint lithography can print patterns on large areas without stitching errors and supports a gamut of structure sizes and shapes, which is a critical to quality criteria for many photonics devices. So here on this image here on the A, here on the A, you can see this is how a stapler will work. So you have a small area of printing area. So you will try to replicate that every single time. Um, and this doing this, I mean, you may have some overlap between what you printed before and what you're printing now, and as is here too, or these are the stitching errors, or also you will have space. So this is a space that you're not using on anything. This is wasted space. So what happens, what does nanoimprint lithography? So what it does is that just using one huge full field imprint, you will do it all at once, and then what you will get, you will get a uniform imprinted image of your desire. So as you can see here, we don't have any space, we don't have any stitch errors. It saves all of that money, it saves all of that time, it saves all of that space for your into your production line or into um, into a process that you would like to implement. All right. Another research example is pattern media. Pattern media has become a great tool or technique to increase the recording densities of hard disk drives. So, on this research that they did, they got to um, get to record up to 3 terabytes of record density. So today's hard disk drives have some recording densities of zero point 0.5 terabytes per square inch. So if we can improve this to 1 to 1.5 terabytes to square inch, maybe it may not be feasible if the same granular method is implemented. To do the today's hard disk drive, they use a granular method that it just wastes a lot of space. So the technique that they discuss in this research is that they store data in a uniform array of magnetic cells that each one of those cells contain 1 bit. This is a huge deviation of what they do, right? So group of randomly magnetic nanograins arranged in a thin film magnetic alloy get implemented, and after that they do the entire imprint. Okay, this is how you do the process using nanoimprint lithography. Okay, so nanoimprint lithography, what it can do, so it can provide the high throughput and precision that is needed for this technique. Nanoimprint lithography will create the magnetic cells lithographically patterned in order arrays, and this will decrease the signal to noise ratio, and each individual magnetic cell can be used as a bit. So yeah, so on this image here, um, you can see here on A and B, this one's here. This is the first step of the process. So some tiny pillars are patterned into a surface. That's what we're seeing here. All these are pillars. So after that, here is the second step. So the second step consists of uh, the deposition of a magnetic film that it's deposited onto the posts. So, and this turns them into some magnetic bits. So all of this is a magnetic bit. Okay. All right. So, some challenges of these research examples. So on photonics, we do have optical nonlinearity and photonic crystals. What does this means is that um, as a replacement in the meantime for photonics crystals, so we need to develop an optical nonlinearity, because right now to everything it kind of goes by the linearity, and in order to get some photonic crystals that can play they do play an important role in enabling future applications such as optical computing, we need to have optical nonlinearity. Okay, so and that's also why I'm also mentioning some photonic crystals. So we need to continue moving forward and develop these photonic crystals. Okay, so these three-dimensional photonic crystals. So yeah, and this is more talking about commercialization. Okay, on pattern media. So the researchers made some huge predictions about the future production of high density pattern media devices. Okay, here the problem is, I mean, they got to a huge um, density, but this still needs to be characterized. It haven't happened yet, and uh, as we know right now, we still don't have that much technology to characterize such great and huge uh, storage density. Okay. All right. So some challenges of nanoimprint lithography. So surface planarity of the attached flexible mold, cost and cycle time when implementing multiple patterning, throughput. Um, this is throughput is interesting because it's also one of its advantages over other lithography techniques. But here we're focusing on that. We need a second filling to get a high throughput. Okay, so this costs times, this costs also more money, but it's still lower than other lithography techniques. Okay, so we have overlay, we have defectivity, so even way that we don't we can go out of the um, stitching errors that other lithography techniques produce. We do have also some protrusions and some hollows created by nanoimprint lithography. Okay, this is minimum, but it does happen. Okay, and the last challenge will be mask infrastructure. Summary. So nanoimprint lithography, it offers a lot of technical advantages in resolution, overlay accuracy, and design of tools. So ultraviolet nanoimprint lithography, UV nail as known, so is one of the emerging tools for nanoimprint lithography that have a lot of potential for future implementations. As we discussed it in this presentation, I mean for photonics and optics, UV nail, it is the future in terms of lithography. Okay, so nanoimprint lithography is affordable and can replace or complement conventional lithography techniques. Okay, and even though it provides a really significant lower processing cost compared to other nano patterning methods, which is preferable for LED manufacturing, like for example. Okay. So these are the references that I use on this presentation. So guys, thanks for watch. Um, if you guys have any questions, you are more than welcome to email me. Um, I appreciate your time, and thanks for watching this video. Okay, guys, bye.